Electrician Program, Chapter 2, Modern Residential Wiring, 9th edition, lessons by H.N. Holzman, lessons edited and narrated by Hector Vladimir. Again, this is Chapter 2, Electrical Energy Fundamentals. Objectives: explain the electron theory for current, explain conductors and insulating materials, define and explain the difference between direct current and alternating current, define basic electrical terms, describe the makeup of an electrical circuit, differentiate between series and parallel circuits, apply Ohm's law to resistance, voltage, and current, explain Ohm's law and give its formula, apply the basic power formula to power, voltage, and current, explain the basic power formula and give its formula, and explain electromagnetic induction, discuss the operation of electric motors, discuss electric power transmission, and explain the operation of transformers. Some of the technical terms that we will discuss in this chapter are alternating current or AC, amperage, ampere, anode, atom, battery, basic power formula, branch, cathode, circuit, complex circuit, conductor, current, cycles, direct current or DC, dry cell, electrical potential, electrolyte, electromagnetic induction, electromotive force, electrons, energy, equilibrium, Fleming's rule, free electrons, generator, Hertz, insulator, joules, Joule's law, kilowatt hours or kWh, left hand rule, load, neutrons, ohms, Ohm's law, parallel circuit, power, primary winding, protons, resistance or R, secondary winding, series circuit, step down transformer, step up transformer, substation transformer, voltage, amperes or volt amperes or VAs, volts or V, wattage, watts or W, wet cell, windings, and finally work. Electron theory. According to the electron theory, all matter is made up of atoms. An atom is the smallest particle of an element. If you take an atom apart, it will not be recognizable as its original element. You can look at each atom and say, this is the building block of copper, for example, or this is the atom of hydrogen. Each atom has a nucleus or center made up of protons, positively charged particles, and neutrons, particles with no charge. Negatively charged particles are called electrons, which orbit the nucleus. See figure 2-1. The electrons are attracted to the protons in the atom. This attraction keeps the electrons in orbit. There can be one or more electrons traveling around in any one atom, and they can be at different distances from the nucleus in their orbital paths. Electrons have the ability to travel from one atom to another. In some types of matter, electrons are tightly bound to the nucleus and travel only with great difficulty. In other types of matter, the bond is so relaxed that moving is easy. These easy moving electrons are called free electrons. Electron travel. A material in which electrons move easily is called a conductor. A material in which movement is difficult is called an insulator. Pure metals, carbon, and most liquids are excellent conductors. Among good conductors are dry gases, glass, rubber, mica, silk, and cork. According to the commonly held electron theory, metals conduct electricity well because they have a great number of free electrons. In insulators, there are few, if any, free electrons. Thus, little or no electricity is conducted. Equilibrium. If a conductor such as a wire connects a negatively charged body to a positively charged body, the electrons will be attracted to the positive particles. Nature prefers everything to be neutral, equal numbers of positive and negative charges. As a result, electrons will flow from the negatively charged body to the positively charged body. See figure 2-2. This flow is called current. Even if two negatively charged bodies are connected in this manner, free electrons will flow from the body with more electrons to the one with fewer electrons. Flow will continue until both bodies have an equal number of electrons. This balance is called equilibrium. Electrical potential is the ability to provide free electrons. Bodies with different concentrations of free electrons are said to be at different potentials. In electricity, differences in potential are measured in units called volts. Types of electric current. There are two types of electric current, depending on the direction of the current flow. The first type is called direct current, or DC. In this type, current flows in one direction only. Direct current is used in battery-operated devices such as radios, flashlights, and automobiles. The second type of current, alternating current, or AC, continually reverses the direction of flow. This constant change in direction is represented by a sine wave. In figure 2-3, in the United States, the standard current is 60 cycles, also known as 60 Hertz. Hertz is a term for frequency, meaning cycles per second. The cycles occur at a frequency of 60 Hertz, thus there are 60 complete cycles in every second. Notice that the direction changes twice in each cycle. This means that the current reverses its direction 20 times each second. This happens so rapidly that the changes generally cannot be detected, not even as a flicker in an electric light. Various cycles and voltages have become the standard in different areas of the world. Seen on your screen are some of the different definitions. Follow along as you go through the chapters. We will not be going through each individual definitions as shown, but we'll be going through the definitions as we read and narrate the lessons. Brief history, as it is interesting to know the history of some of the electronic and electricity pioneers and inventions and technologies and its developments. The evolution of electrical standards. North American electric systems did not use 120 volts AC or VAC and 60 Hertz in their early days. Thomas Edison was using and promoting DC power in his early electric distribution systems. There were problems with DC. However, it was not very easy to change the voltage, so transmitting more power meant higher current in the wires. The current became so high that the wires were actually melting from being overloaded. Due to the high currents, there were large losses due to voltage drop over short distances. It was also very inconvenient to use devices that required different voltages. Nikola Tesla championed the use of AC systems. It was easy to change the voltage so that large amounts of power could be delivered by increasing the voltage and decreasing the currents in the wires. With lower currents, the wires would not overheat and melt. Losses due to voltage drop were greatly reduced, meaning that the electricity could be transmitted over much longer distances. Tesla had the backing of George Westinghouse, who also had the financial backing of John Jacob Astor and J.P. Morgan. Edison tried to prove how unsafe the AC system was by holding public electrocutions of animals, including Topsy the elephant. He went so far as to have two of his employees invent the electric chair to demonstrate how effective AC was at killing people. Ultimately, the Westinghouse AC system won the battle based on its technical superiority, and Edison's General Electric Company changed from DC to AC. It is less clear how the frequency of 60 Hz was adopted, but it seems that it was a high enough frequency that the human eye could not see light bulbs flickering at 60 Hz. Tesla had calculated that 60 Hz was the most effective frequency, but his early systems were originally 240 volts. Other countries adopted 50 Hz because it was still too fast to see the flicker, and it matched the 1, 2, 5, 10 standard popular with the metric countries. Sources of electrical energy. To maintain a flow of electrons or electricity, it is necessary to have a source that is always at greater electrical potential. That is, always has an excess of free electrons that are ready to move along a conductor to where the electrical potential is less. The energy may be produced chemically, as with a battery, or mechanically, as with a generator. Battery. A basic chemical device for providing electrical power is the voltaic cell. On your screen, figure 2-4 shows a simplified cell made up of two metal plates suspended in a mild acid solution. The plates react chemically with the acid. Electrons on the surface of the copper plate are stripped away and travel to the zinc plate. Then the copper plate has fewer electrons and is positively charged. The copper plate becomes a positive pole or anode. The zinc plate has excess electrons and becomes the negative pole or the cathode. It is common practice to group a number of cells in a single container, such as the one shown in figure 2-5. A group of cells is called a battery. A wet cell battery uses a liquid chemical. A dry cell battery uses a somewhat dry chemical paste. The liquid or paste is called an electrolyte. When the battery is connected to a circuit, current will flow through the circuit from the cathode to the anode. Generator. A battery is just one of the ways to generate and drive an electrical current. A second method is with a generator. Driven by some mechanical force, a generator is a device that creates differences in electrical potential between two electrical poles. It moves electrons from one terminal and deposits them into the other terminal. This is accomplished through electromagnetic induction. This process will be explained later as we discuss generators and alternators. Measuring electricity. Measuring electricity is essentially finding how much, how fast, and with what force the electricity flows through a conductor. Terms or units used to measure electricity are amperage, voltage, resistance, and wattage. The full definition of these terms is vital not only to measuring electricity, but to understanding its very nature. Current. The flow of electricity, as you have learned, is called current. The rate of this flow is known as amperage, represented in the equations by the letter I. The ampere, or capital A, or amp, is the unit used when measuring current. The equipment where electricity enters a house is usually rated at 100 amps or 200 amps. Voltage. The pressure or the electrical potential that moves electrons through a conductor is called voltage or electromotive force. E or EMF. Its unit of measure is the volt. Most residential wiring is rated at 120 volts and 240 volts. Resistance. The opposition to the flow of electrons through a conductor is called resistance, represented with a capital R, or as you will learn, as an omega, which is a Greek symbol. And it is similar to friction. Resistance is similar to friction. This electrical resistance is measured in units called ohms. Like other forms of friction, resistance is responsible for creating heat and consequent loss of power. All devices that use electric power are forms of resistance. Power. Power, represented by capital P, is the rate of doing work, and in electricity is measured in watts, represented by capital W, or volt amperes, VAs. Power determines how fast a certain amount of work can be done, or determines how fast a certain amount of energy is consumed by a load. Watts are relatively small units, and we often speak in terms of kilowatts, that is per 1,000 watts, and megawatts, that is per million watts. Work. Work is the measure of how much power is applied or consumed over a period of time. Work is measured in joules. 1 joule is 1 watt per second. Electrical energy in particular is measured in power time units called watt hours or kilowatt hours, kWh. 1 kilowatt hour is equivalent to 1,000 watts of power being used for 1 hour, which is the measure of time. Figure 2-6, as seen on your screen, is the summary of these electrical terms. Circuits. No electron flow will occur unless there is a pathway in which the electrons can move. In a water system, the pathway is the piping, which moves the water from storage to where it is used. In electrical devices, wires form the pathway, which is called a circuit. See figure 2-7. The circuit allows the electrons to flow through its conductors as long as the power source supplies the electricity. A simple circuit consists of the following elements: a power source. For a residence, the power source could be considered the electrical generating stations. However, the primary sources include small generators and batteries. Conductors. The wires provide a path for the current to travel. The loads. These are devices through which the electricity produces work. The devices for controlling the current. These devices include switches, fuses, and circuit breakers. Types of circuits. The two basic types of electrical circuits are called series and parallel. A third, called a complex circuit, is just a combination of the two. Series circuit. In a series circuit, only one path is provided for the current to flow. The electricity flows through every device in the circuit. If one device is burnt out or open, the circuit will not function. See figure 2-8, which is a simple circuit diagram of a series circuit. Apart from switches and fuses or circuit breakers that are used to control the flow of electricity, series circuitry is not practical for residential wiring. A simple example will explain why. older Christmas trees lights were often wired in series. Current had to pass through every light bulb for the string of lights to work. If one bulb burnt out, all the lights went out. Past the burnt out bulb, that is. Finding the defective bulb was a trial and error operation. Each bulb had to be removed and tested. Residential circuits are set up so that a malfunctioning or non-functioning load will stop the electrical current in the remainder of the circuit. Parallel circuit. The parallel circuit has more than one path available for the current to flow. See figure 2-9. Like the series circuit, the parallel circuit has a complete path for the current to follow. Each path goes to a load that can operate independently if the other branches and loads in the circuit were to fail. If one load, such as a lamp, burns out, the other branches would continue to operate as long as they're okay, since a path still exists from one supply terminal through the circuit to the other supply terminal. Under normal conditions, another advantage of parallel circuits is that the current draw of each branch affects only that branch. In a series circuit, current draw in one load affects the rest of the loads on the circuit. Loads such as lamps, heaters, or motors might not operate properly in a series circuit. Except for switches, fuses, and circuit breakers, all residential wiring is done in parallel. Loads. In electrical systems, a load is any device that uses an electric current and converts the energy to another form. Loads include lamps and light bulbs, which convert electrical energy to light, electric furnaces and space heaters, which convert electrical energy to heat, power tools and motor-driven appliances, which convert electrical energy to mechanical energy. Radios, televisions, and other electronic devices convert electrical energy to sound. Each load is designed to operate at a specific voltage. A voltage rating is given with every device. It is important that the device to be operated at its rating. Otherwise, the device can be damaged or even destroyed. In some cases, the entire circuit could be damaged. This is an important reason series circuits are not used in residential wiring. Circuit fundamentals. Electrical circuits consist of a source of electromotive force, or EMF, and one or more complete pathways of electron flow. Both DC and AC circuits require a definite pathway to be useful. A circuit normally consists of a power source, protective devices such as fuses or circuit breakers, one or more loads, a switching device, and conductors. Electrical resistance, Ohm's law. To understand circuit theory, you must understand electrical resistance. Without it, electrical current could create neither heat nor light. George Simon Ohm first explored resistance in 1827. He expressed the relationship between current, voltage, and resistance. He said current in a circuit is directly proportional to the voltage applied to the circuit, and it is inversely proportional to the resistance of the circuit. This statement is called Ohm's law. This law can be applied to the entire circuit or to any part of the circuit. Mathematically, the law takes the following form, as shown on your screen, where I is the current measured in amperes, E is the voltage or EMF, electromotive force, measured in volts, and R is the resistance measured in ohms. Electrical power, basic power formula. A load in an electrical circuit consumes energy. The rate at which it consumes energy is called power. The relationship between power, voltage, and current was established by James Watt and is called the basic power formula. It states that, as shown on your screen, P equals I times E, or power equals current times voltage, where P is power measured in watts, I is current measured in amps, and E is EMF measured in volts. Series circuits. The series circuit has only one loop or path. When devices such as resistors are in series, they are placed one after the other, so that the current flows through all of the items or resistors, each in succession. The three resistors, as illustrated in 2-10, are in series arrangement. Series circuit rules. The series circuit follows certain rules that could be summarized as follows. The total resistance, RT, is the sum of the individual resistances. Therefore, the total resistance of the series circuit in figure 2-10, which we'll show here momentarily, is as shown on your screen, where RT equals to RA, R plus RB plus RC. The current amperage of a series circuit is the same throughout. Thus, the total current, or IT, of the circuit is the same as the current running through each load. By applying Ohm's law, we can find the current in figure 2-10. Therefore, 1 amp is not the only total amperage, but also the amperage flowing through each of the resistors. So it is the same throughout. The total voltage at the source is equal to the sum of the voltages of the resistances, or the voltage drops at each resistor. The voltage at each load is calculated using Ohm's law, where voltage over a resistor A equals the amperage A times the resistance A, as seen on your screen. The same goes for voltage at resistor B. It's the amperage B times resistance B. Same for resistor C. Amperage at resistor C times resistance C equals your voltage at resistor C. So the total voltage, or ET, then can be calculated by adding the voltages for all loads, or ET equals voltage at A plus voltage at B plus voltage at C, which gives us, in this case, 6 volts. A break anywhere in the circuit stops the electron flow for a series circuit in the entire circuit. This is the main disadvantage of the series circuit. Ohm's law applies to any part of the entire series circuit. A quick example, as shown on your screen, using the circuit shown in figure 2-11. Find A, the total resistance, or RT, B, the total current at the source, or IT, C, the voltages of resistors 1 and 3, E1 and E3, and the solution is to first step A is to add the individual resistances to find the total resistance at RT. This is the circuit we're talking about. Step B is the current in a series circuit is constant, Therefore, the total current, or IT, equals to the same current of resistor 2, or IT. The current at resistor 2 can be found using Ohm's law, as shown. IT equals I2, which equals to E2 divided by R2, which in this case is 3 amps. Continuing on to step C, the current through each resistor is equal to the total current, or 3 amps. Use Ohm's law to calculate the voltage at resistor 1 and 3, which, following the formula, gives you 60 volts for E1 and 90 volts for E3. You can also check to see if the total voltage is equal to the sum of the individual voltages. Following the steps, ET equals IT times RT, which gives us 180 volts, and ET equals V1 plus V2 plus V3, which gives us 180 volts again. Parallel circuits. As we learned earlier, a parallel circuit is an electrical circuit having two or more different conducting pathways. The term parallel in electricity does not necessarily mean physically or geometrically parallel, but simply alternate routes. Each of these alternate routes is called a branch. Parallel circuits are more commonly used in electrical circuitry for reasons that will become clear as we go on. Figure 2-12 shows a simple parallel circuit containing 3 resistors. Arrows indicate the electron flow. Parallel circuit rules, like series circuits, parallel circuits follow certain rules. A break or opening in any branch of a parallel circuit does not stop the flow of electrons to the remaining branches. The voltages across all branches of a parallel circuit are the same and are equal to the voltage at the source. That's very important. The voltages across all branches of a parallel circuit are the same and are equal to the voltage at the source. In figure 2-12, which we'll look at in a moment, the voltage in branch B is 120 volts. Therefore, the voltage in branches A and C are also 120 volts. So mathematically, the source voltage, branch A voltage, equals to branch A voltage, which equals to branch B voltage, which equals to branch C voltage. Ohm's law applies equally well to the total circuits or any of the loop or branches. The total current IT is equal to the sum of the currents flowing through each of the branches for figure 2-12, which we'll see here in a second. The total resistance in a parallel circuit is the reciprocal of the sum of the reciprocals of the separate resistances in a parallel. For that, just look at the formula. You'll get a better idea. Now, before throwing up your hands, let us look at this mathematically, which is 1 divided R total equals to 1 divided R branch A plus 1 divided R branch B plus 1 divided R branch C, which could be written as the formula shown, which is RT equals to 1 divided by 1 divided R A plus 1 divided R B plus 1 divided R C. Now use the resistance information from the circuit in figure 2-12, which we'll see in a moment. Find a common denominator, and we get RT, or resistance total, equals to 10 ohms. You can review these by rewinding the video or by looking at the lesson in your text. Series parallel combination circuits. Practical circuits, for the most part, are far more difficult than those just outlined. Quite often, loads are in a particular circuit are designed in both series and parallel configurations. When loads are arranged both ways in a single circuit, the circuit is called a complex circuit. An example of this type is shown in figure 2-13. We will use this circuit to show the steps taken to simplify a complex circuit. The circuit is shown, again, 2-13. The source is 12 volts. The resistance of each component resistor is also given. First, we need to find the total resistance. To do this, we must reduce the parallel resistances into equivalent single resistances, which we'll call Req, and add this resistance to the resistances arranged in series. The equivalent resistance from the parallel portion of the circuit can be said to be 1 divided Req, which equals to 1 divided R3 plus 1 divided R4. Working out the equation, we get 4 ohms. We may draw a simpler equivalent circuit showing the equivalent resistance in series with R1 and R2. The one shown in figure 2-14. Now add this resistance to resistors 1 and 2 to find the total resistance. In this case, 12 ohms. Having found the total resistance and given the total voltage, we can find the total current through the circuit using Ohm's law. IT equals ET divided by RT, which in this case gives us 1 amp. Next, find the voltages across each of the resistors. Since resistor 1, resistor 2, and the equivalent resistor are in series, the current at each resistor is the same as the total current for 1 amp. Using Ohm's law to calculate the voltage at resistors 1 and 2 and the voltage across the equivalent resistance. Using the formulas provided, E1 equals I1 times R1 equals to 1 volt. E2 equals I2 times R2 equals 7 volts, and voltage drop of the equivalent, or EQ, equals IT times Req, which gives us 4 volts. This is verified by the fact that the total voltage is equal to the sum of the various voltages in a series circuit. All that remains is to find the portion of the total current, 1 ampere, that goes through each of the parallel resistors. Remember, EQ equals to E3, which equals to E4, which equals to 4 volts in this instance. So the current at 3, or I3, equals to E3 divided by R3. Remember, this is just Ohm's law configured in a different way to solve for I, or current, which is 4 volts divided by 6 ohms, which gives us 0.67 amps. And I4 equals to E3 divided R4, which in this case gives us 0.33 amps. Again, verification comes from the fact that the total current, or 1 ampere, is equal to the sum of the current through each branch of the parallel resistors. Thus, 1 amp equals to 0.67 amps plus 0.33 amps. Considered as a whole, electrical circuits are mostly of the complex type. The source voltage is carried by means of wires across every device, appliance, and branch circuit. These are connected in parallel. Circuit summary. Figure 2-15 is a summary of the various circuits discussed in this chapter. Figure 2-16 is a simple aid to remember Ohm's law. Simply cover the part you wish to find and you discover that what you multiply or divide by. Thus, to find E, multiply by R, multiply R by I. To find R, divide E by I. To find I, divide E by R. Power and work. Electric power is a combination of current and voltage. It is actually current times voltage. Power expresses the rate at which electricity is being consumed regardless of the voltage or current. For example, a 120 volt air conditioner drawing 10 amps of current is using the same amount of power as 240 volts air conditioner that is only drawing 5 amps of current. The power in both cases is 1200 watts. Power indicates how fast a certain amount of work can be done. Energy and work are almost the same thing. The work done equals the charge in energy. Work, or W, is a certain amount of power, or P, applied or consumed for a certain period of time, or T, small t, where W equals P times T, substituting E times I for P. So W equals E times I times T. You have 100 watts of light bulb and you leave it turned on for 5 hours. The total power consumed is W times P times T, which is 100 watts times 5, or 500 watt hours. Now you change it to a 250 watt light bulb and you leave it turned on for 2 hours. The total power consumed is, in this case, again 500 watt hours. Both light bulbs use the same amount of total energy because the second light bulb is more powerful. It is brighter and it uses energy faster. Even if we leave it for less time, less than half the time, it uses the same amount of wattage. The electromagnetic induction. In a battery, chemical action displaces electrons and produces the current through a conductor. Current can also be produced by using magnetic fields. Two men working independently discovered they could produce a flow of electrons in a wire by passing the wire through a magnetic field. Figure 2-17 shows this concept. Michael Faraday and Joseph Henry discovered the electromagnetic induction, the process of producing an electromotive force by varying the magnetic field surrounding a conductor. If you were to fashion a conductor into many loops, a coil, effectively, and rotate it between two magnetic poles, you would have a crude generator, such as the one in figure 2-18. The strength of the electron flow in a generator is increased by 4 factors: a greater number of turns or loops of wire in the coil, a faster speed of the conducting loop rotation, an increased strength of the magnets, and positioning the moving coil at right angles to the magnetic field lines of force. See figure 2-19. Generators and alternators. Alternators, like generators, are rotating machines driven by some mechanical force. They use the electromagnetic induction principle to convert the mechanical force to electrical energy. There are AC generators and DC generators. The AC generator is usually called an alternator. Direction of induced current. Current from a spinning generator will always move in a specified direction. You can determine this direction by knowing the left-hand rules. The left-hand rule for generators, figure 20. Point your thumb, forefinger, and middle finger of the left hand at right angles to each other. According to the rule, the thumb is pointing to the direction the wire is moving. The forefinger is pointing in the direction of the magnetic field, north to south, and the middle finger is pointing in the direction of the induced electron flow. This statement is also known as Fleming's rule. Alternating current generator. The AC generator or alternator consists of several distinct parts, such as the one in figure 2-21. Each has a specific function. The coil or armature. This part rotates and it has the conducting wire that cuts across the magnetic field. The electron flow begins in the coil. The non-moving magnetic poles. These poles create a magnetic field. In some generators, the poles are magnetized by a portion of the generated electrical current. Slip rings. These metal rings are connected to the ends of the coil wires. The slip rings rotate with the coil and transfer the current to the brushes. The brushes, which are two brushes connected that are in contact with the slip rings, and transfer the current from the slip rings to the external circuit. One brush is in contact with each slip ring. As the armature is turned, it cuts through the magnetic field created by the field magnets. Electrons flow through the wires of the armature. The electrons move into one of the slip rings, then to one of the brushes, and then finally to the external circuit, such as the one in figure 2-22. With every half turn of the armature, the electron flow reverses, following the left-hand rule. Then the electrons flow out of the external circuit through the opposite slip ring and brush. This creates the reversal of electron flow, which accounts for the alternating current. The speed at which the generator is turned determines the frequency of the current. One complete turn is a cycle, and 60 turns each second create a 60 Hz electric current. Direct current generator. The DC generator is similar in construction to the alternator, except that the two slip rings are replaced by a single slip ring with two halves, commonly called a commutator. The two segments of the commutator are connected to the two ends of the armature, such as in figure 2-23, and rotate with it. As the armature rotates, an alternating current is set up in the coil, exactly as the alternator. However, because the segments of the commutator change brushes every half a turn, the AC coil is changed into a pulsating DC in the external circuit. See figure 2-4. The single-phase and three-phase electricity. An AC generator may produce either single-phase or three-phase electric power. A generator with a single armature or coil produces single-phase power. To produce three-phase power, the generator must have three armature coils. The coils of a three-phase generator are located exactly 120 degrees apart. During each turn of the rotor, voltage is created at three different intervals. The separate voltages or phases are said to be 120 degrees electrically apart in time, or 120 degrees out of phase. Power plants generate three-phase power because it is more efficient. The electric power is converted to single-phase for residential use. Three-phase power is supplied to commercial and industrial customers for either of the following reasons. Three-phase power is necessary for high-demand applications and cost-effective where there are many motors. Three-phase motors are simpler, less expensive, and more powerful than single-phase motors. Electric motors. Electric motors, such as the ones shown in figure 25, are like generators. They transform one kind of energy to another. While generators convert mechanical energy to electrical energy, electric motors change electrical energy back to rotating mechanical energy. A DC motor is constructed exactly like a DC generator. The rotation takes place when the polarity of the armature is in opposition to the poles of the field magnets. In other words, like magnetic poles in the rotor repel each other to start the rotation. Constant shifting of the magnetic polarity keeps the motor spinning. AC motors are somewhat different in construction, but their operation is similar. These motors will be discussed in a later chapter. Transformers. A transformer is a device that uses electromagnetic induction to change the voltage as it transfers electrical energy from one circuit to another. Basically, a transformer is made up of two coils of wire wrapped around an iron core. See figure 2-26. There is no connection between the two coils of wire. Each is linked to a different circuit. These coils are commonly known as windings. The coil that is connected to the power source of a transformer is called the primary winding, or primary. The coil connected to the load side is called a secondary winding. The current in the primary winding creates a magnetic field. That induces current in the secondary winding. The voltage out of a transformer is directly related to the number of turns of wire in the windings. If there are more turns in the secondary winding than in the primary winding, the voltage out will be greater than the voltage in. Such a transformer is called a step-up transformer because the voltage steps up or increases from the primary to the secondary. In fact, the change in voltage from primary to secondary is directly proportional to the change in the number of wire turns. Looking at the formula in your screen, suppose that the incoming electrical power is at 110 volts on a transformer that has 100 turns on the primary coil and 600 turns on the secondary coil. The secondary coil has 6 times as many turns as the primary coil. Therefore, the output voltage will be 6 times greater. In a step-down transformer, the secondary coil has fewer turns than the primary coil. Therefore, the output voltage is less than the input voltage. Electrical system overview. The electricity is generated at large power stations. These stations have huge generators that are spun by a turbine. High pressure steam causes the turbine to spin by blowing past the turbine blades. A turbine looks like dozens of fans all collected or connected to the same shaft. If you think of the wind causing a windmill to turn, then you have the right idea. The steam is produced by boiling water in a boiler. The heat for the boiler can come from many sources: natural gas, coal, oil, and uranium for nuclear fuel, which are the most common sources. Most electrical power is generated at 24,000 volts, and it is stepped up to 132,000 volts, or 238,000 volts, or even 345,000 volts at the power station. The electricity is sent out to substations over high voltage cable. A substation is a collection of transformers located away from the power station that lowers the voltage of the electrical power and redistributes it along another set of conductors or distribution lines before being brought into homes. The voltage is further reduced to 120 volts and 240 volts. From the point of generation up to the service transformer, the power is all three-phase power. Your service transformer is connected to one of the three phases, while your neighbor's transformers are connected to other phases. The houses are split up among the different phases in order to keep the load on each phase balanced. The power enters your house through the service entrance, which is where the electric meter is located. The electric meter records the amount of power you use each month. The electric company reads the meter every month and charges you for the amount of energy used. After passing through the electric meter, the power passes through the main disconnect switch or panel. This is where the power is divided up into branch circuits for the different parts of your house. The panel contains circuit breakers, which will shut off the power if a circuit becomes overloaded. Individual conductors are connected to each circuit breaker and are further connected to the light switches, devices, equipment, and receptacles in your home. The electricity thus reaches your lights, stereo, computer, toaster, and other devices that convert it into forms of useful energy. That is the end of the lesson. Next are review questions. Electricity is a form of energy. Substances that allow electricity to pass through an item through them easily are called conductors, whereas those that block the electron flow are called insulators. Question 3. There are two types of electric current we use, and they are called alternating current and direct current. Question 4. A conductor is the pathway for electric current. Question 5. In a series circuit, current must go through every device in the circuit or it will not work. Question 6. The load in the circuit shown are connected in parallel. Question 7. What did Faraday and Henry discover? They discovered the concept of electromagnetic induction, or the electrical generator. In what important way do AC and DC generators differ? There's a few ways to answer this, but the answer I put was DC generators have a commutator or a combined slip ring, and AC generators have two separate slip rings. Question 10, a transformer uses blank magnetic induction principles to increase or decrease voltage between an electrical power source and its load. Question 11, Ohm's law relates to resistance, current, and voltage in an electrical circuit. Question 12, the basic power formula relates to power, voltage, and current in an electrical circuit. Basic power formula is P equals to E times I. Question 13, a series circuit has a current of 2 amperes. What is the source voltage in the total resistance? And if the total resistance is 6 ohms, and I have put the formula of voltage total equals to current times resistance. So in this case we have 2 amps times 6 ohms equals to 12 volts. Which of the following graphs would best express the correct relationship of resistance to the other conductor characteristics? So let's look at the graphs. First graph, the resistance increases as the conductive diameter increases, which is not correct, and the resistance decreases as the conductor diameter increases, which is correct. B is correct. Question 15, what is the total amperage of a parallel circuit having a total resistance of 12 ohms and a source resistance of 24 volts? And we simply use Ohm's law formula where I equals E divided R. We substitute E by 24 and R with 12 ohms, and we get 2 amps. Question 16, true or false? Ohm's law applies to series, parallel, and complex circuits. Absolutely true. Question 17, power is the rate of doing work, and that is true. Question 18, electrical energy is measured in units called kilowatt hours, or kWh. Know the code. The first issue of the National Electrical Code is published in what year? The National Electrical Code is published by what organization? That would be the NFPA, the National Fire Protection Association. What is the primary purpose of the National Electrical Code? And those answers you can find them either on your screen or on your text. And that wraps up, finishes this chapter, chapter 2. Thank you very much. Look for the next chapter or lesson.